So for our project, we decided to explore the physics of a bouncy ball in free fall. So these two videos just show the demonstration that we were doing for our system. So this right here is the graph that we obtained from the video analysis. There are two different graphs on here. We're going to have the blue line, which is going to represent our position versus time graph. As you can see, it starts with 0. This is because we're holding it above the ground. This is where it hits the ground, and this is when it comes back to the second apex. This red line here is going to be our velocity versus time graph. That's why it's going to be a bit more steep than the blue one is. This really large red line here is where we chose to calculate our slope for the velocity graph to find our acceleration. And as you can see right here, our acceleration was negative 8.88 meters per second, which is pretty good. However, it is not exactly the 9.8 meters per second. That is free fall acceleration. It's about a meter per second off. We determined that this is most likely due to the fact that we had to manually place every tracking point within the video analysis system. So it was most likely a human error on part of us. We may have not always put the dots in the correct place. Sometimes just due to the quality of the video, we had to estimate where we were going to put it. So the big question of this project is, why is the energy conserved within this system itself? So it all comes down to the law of conservation of energy, and for us it's specifically an isolated system, so we do not have any work. So for ours, we were looking at the kinetic energy, the gravitational potential energy, and the change of thermal energy. This is for considering how the ball is before the bounce and after the bounce. We used the gravitational potential energy equation to calculate it, and we determined that after our collision, the gravitational potential energy is actually going to be 4/5 of what it was originally. So over here, it just gives a little kind of layout of how the energy is transformed throughout the entire system. First, it starts as gravitational potential energy, becomes kinetic energy. Then about 80% of this kinetic energy has become elastic potential energy when the ball finally collides with the ground. However, 20% of it is going to be changed into thermal energy because the friction that is created between the ball and the ground itself. This energy is going to be energy that technically becomes lost since it cannot be transformed back into potential or kinetic energy. So that 80% of the elastic potential energy is going to change back into kinetic energy. And finally, that kinetic energy will become gravitational potential energy once again when the ball finally reaches this apex of the second bounce. So this here just shows the two tables of our values for the energies that we calculated both before the collision and after the collision. You can see the initial height and the final height, the initial kinetic energy and the final kinetic energy. Since we're considering it when the ball's at its maximum height, both of these are going to be 0. We're going to see the initial potential gravitational potential energy and the final gravitational potential energy, and we're going to see that this change of thermal energy here is the 20% of kinetic energy that was lost during the collision. But also, it's going to add up to the same exact total as from before and after, so energy is conserved. Bouncy ball is elastic, and this is what allows it to conserve so much of its kinetic energy as opposed to having most of it dissipate into thermal energy. It's not completely elastic, only nearly elastic. If it was completely elastic, we would see that 100% of the energy of this kinetic energy is going to be conserved, which was not the case. So we concluded that energy is going to be conserved in an isolated system of a bouncy ball that is in free fall. Though nearly all materials are elastic in some way, the high elasticity of a bouncy ball itself is what's going to allow it to conserve such a large percentage of its energy during a collision. And this is the end of our presentation.